Okay, Cation Analysis lab. So this lab used to be a 3-week lab, so it's kind of written up in a way, and I'll describe it just to give you some context. And it talks about that it's combination of Le Chatelier's equilibrium lab and then be able to do calculations for uh, equilibrium QSP and KSP calculations. And so putting those together. And so what we used to do is have it as a 3-week lab. And so the third week was the lab practical, similar to what we use the group projects currently. And so the idea behind it is that you would collect data the first 2 weeks, just doing the same thing you're doing this one, but with different counter ions. And then afterwards, you collect all the data, then you can come up with a scheme to be able to separate these 3 ions. This would be the pre-lab, and then lab would be separate 7 ions. And based on your data, you would figure out what would you add and how many drops in order to precipitate one thing. So in this one, looking for something that hypothetically could precipitate potassium ions. And that would leave behind barium zinc. Now you find something else that will separate barium and zinc. And so then once you have that, you can always get some false positives. So we always look for confirmation, either redissolve, do a new precipitate or something like that, some change that will also confirm whether or not this was potassium and barium and zinc. All right. And so what they would do is they would collect all this data and then they would combine kind of reduce it down to fill in this table, something like this. And that would allow them to come up with a scheme like we were describing. So that's why it talks about observations are critical. So if you really got good detailed observations just from your group projects, you don't always know exactly what you need. So more is better, and then you can trim it down with it. All right. And so this lab's an individual. You need to each do your own, like adding and dishing, right? Record your observations, but in doing the calculations and conclusions, we want you to talk with your neighbor. But again, everything you turn in has to be a reflection of your work and your abilities. All right, so in the pre-lab, it walks you through how we do this. All right, so if we hypothetically mix these together, and then there's a hint that further on, there's this language that further explains this, how we do these calculations. And so we're going to mix copper nitrate and sodium hydroxide. So we usually write out the equation, and then the reaction possible is the swapping of the counter ions. So these are the only possible products. And taking advantage of solubility rules, sodium nitrate would be the last precipitate. So really, if we're looking for precipitate, it would be this case here. And so if we're going to make a prediction whether or not it precipitates, what we look at then is the QSP of that copper hydroxide. And the question is, are those concentrations greater and give a QSP greater than the KSP? And so we can't just use the concentrations here because that's before it's mixed, and we need the equilibrium concentration when we're doing this reaction. So you have to do M1V1 equals M2V2, or this is another form of it to find the new concentration of the metal of the hydroxide. And now we can plug it into here, this QSP, based on the formula here, to give us the QSP, and we can compare that with the KSP. If there's no KSP given at the end of the lab, then you'll just assume it has a high solubility and it's not going to precipitate. All right, so you'll do that for the case, and then you don't have to redo this all, because for all the 2+ ions, it's the same QSP, right? Because they're all the same metal, all the same volumes, and so on. And the difference between lithium and iron here is that charge. So for lithium, this would be 1, and then for iron, this would be 3, based on the formula of the hydroxide you're thinking about precipitating. So very redundant calculations. Again, we want you to show the steps, kind of communicate it clearly, but in a clear and concise manner. Now, at the end, you'll find the KSP values. That's the main thing you're going to be referencing. And so it gives you the equilibrium. You can copy and paste. This, again, was left over from the 3 labs that we used to do. And you can just screenshot and grab this for those equilibriums. But if you're writing it by hand, you do need to rewrite them. And then here, this are KF, so they're all aqueous. And so you're going to do your main comparison here. When things don't work, then that's where you're going to come over here and see if this explains why it didn't work, and so on. All right, so first you explain with color. I talk about this in pre-lab, how color can be misleading. And then you're going to go on, do the precipitations with sodium hydroxide. And then it's a strong base. Hopefully you can determine the concentration of the hydroxide present. And then compare that with the hydroxide present in pure water. All right. And so you should know this. You have two routes with KW or doing pH to POH and so on. Here's the language for the determining the QSP and the screenshot I showed you earlier. And then you start doing it with all the metal ions. All right. So first you calculate the QSP for all these and then compare with the KSP. Once you do that comparison, that's where you're going to decide, is it under equilibrium or non-equilibrium conditions, meaning that it's just going to be soluble, no precipitate. Then you test your predictions. You want to kind of clearly communicate your observations. And then you're going to do a calculations if you add 2 mils of excess sodium hydroxide, and then write out the solubility when you do that, and then you can test it. Okay, so now you're going to do the same thing with ammonia, though, which is a weak base. So now you're going to use this Kb and solve for the OH concentration 3 molar. That'll give you the OH, so similar to what the 3 molar NaOH had. And you'll have to do the same dilution calculation. So we ask you to show the how those two equilibrium can come together. You have a lot of different ways that you can do this. You can write out one single step here, and then you can I would use arrows to show how that hydroxide then can combine with the copper to form it. All right, and then here's another way you can do it. So a couple different ways you can show the sorry. All right. So same thing with the ammonia. You have a lower concentration of OH. You're going to calculate the QSP. The same thing, just with that smaller concentration, you need to do the M1V1 equals M2V2, then compare with the KSP, test your predictions, do the calculations again. If you add 2 mils of excess, so new M1V1 equals M2V2, the metal you already know from the first part, you just need that hydroxide from the ammonia for the second part, and again, test your predictions. Okay, so final step here is you're going to keep those hydroxides and then try to dissolve them with acid. So in theory, from the equilibrium lab, we should be able to push this either way. If we add more hydroxide, then we drive it this way. If we remove hydroxide by adding acid and neutralizing it, we could drive it the other way. So you choose one and show how the addition of a strong acid can dissolve the precipitate. And then you're going to test it with the two acids. So you have HCl and nitric acid. So you know how many drops of 3 molar sodium hydroxide. You just want to add enough to compensate it. All right. So the same volume of nitric or 3 times the volume of hydrochloric. So the second to last part, the flame test, then you're going to have a station set up, and you're going to have to look through this spectroscope line up. I'm going to describe this in the pre-lab lecture a little more, but you're going to look through here. You're going to line up with that slit with that flame, and then you're going to turn your head and look over here at that diffraction gradient and see where those lines are on that. And then you'll try, one will be easy, the second will be harder. And so what's happening is I'm bubbling a metal salt through there, and it's going into the Bunsen burner, and the Bunsen burner is heating it up and going to excite the electron. And as the salt moves to the cooler part of the flame, it's going to fall back down to energy and give off a photon that corresponds with the energy change for it. And we get these really sharp lines for atomic spectra, and we can look at emission, or if we have the metal salt in the vapor, and then we can look at absorption. And this is how we can detect in clouds and other planets and on the sun what elements are there. So this is the setup. So you'll find 2 Bunsen burners, and you'll have the one solution bubbling into one to the other, and you just record the color of flame. Then you use the spectroscope and try and see the line spectra. And like I said, one is easy, one is harder for it, and hopefully you can see both. And then you'll use this animation, and here you can click on the different metal so we can see that the color of the flame is only due to the metal, not the non-metal, and the corresponding line spectra. And now hopefully you'll be able to match up from the simulation in your data and identify what metal salts in that Bunsen burner. Oops. All right, and so use the simulation, answer these questions. And then the last part is the confirmation test. And this is optional because you actually did this already in the equilibrium lab. And so the idea here is that if we had iron, then if we add potassium thiocyanate, we know it produces this dark reddish brown color. So if we isolate it and then we add this and we see the change goes from the light yellow to this, then that is indicative of iron and so on. And there's another confirmation test if you want to run it and see. All right, as we come to the end of the semester, you should find a folder for the makeup lab and you can sign up for doing the makeup lab. The only thing I say is that if you sign up for it, you need to come do it. It's really annoying when people sign up and we get it set up and then they don't come do the makeup lab. All right.